Okay, in the last class we have discussed about this 2 by 2 multiplier. So, today we will discuss about the 4 bit by 3 bit multiplier, and we are going to show that this can be implemented by using a 4 bit triple carry adder. So, while writing the Verilog code, you can instantiate the 4 bit triple carry adder code. Okay. So, if you consider the 4 bit by 3 bit multiplier, basically I am taking this 4 bit number as B3, B2, B1, B0 into A2, A1, A0. So, if you perform this multiplication, so A0, B0, B1, A0, B2, A0, B3, A0, and if you multiply with A1, B0, A1, B1, A1, B2, A1 and B3, A1. If you multiply with A2, B0, A2, B1, A2, B2, A2 and B3, A2. So, by multiplying this 4 bit by 3 bit number, the number of resultant output bits will be, so this B0, A0 will be directly C0. By adding these 2 bits, you will get C1. So, these 3 bits C2, C3, C4, C5. Here you may get carry from this stage. So, by adding these 2, you may get one carry also. So, totally we require 7 bits. This you can easily verify using this the maximum numbers of this 4 bit and 3 bit. So, the maximum 4 bit number is 1111 in binary into 111 is the 3 bit maximum number in binary. So, this is in decimal, this is 15 into 7. So, this is equivalent to 105. So, to represent this 105 we require the 7 bits. 105 if you divide successfully with 2. So, this is 52, 1 is the remainder, 2 is 26, 0 is the remainder, 13, 0 is the remainder, 6, 1 is the remainder, 3, 0 is the remainder, 1, 1 is the remainder, 0, 1 is the remainder. Till this is 0, you have to continue. The value of this 105 in binary will be, you have to read from bottom to top, 11010001 in binary. So, how many bits are there? 1, 2, 3, 4, 5, 6, 7, 7 bits. So, 7 bits are required. Okay. So, now how to implement this using binary adder? So, basically you have to first generate all these product terms. How many product terms are there? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 product terms are required. So, we can use 12 AND gate produce this 12 product terms. So, basically I am giving first A0 as a line with 4 AND gates, which is common to 4 AND gates. This is A0 line. So, you can give this as the input for one AND gate, whose other input is B0. You can give this input for the another AND gate, whose second bit is B1. This has one bit for the other AND gate, whose other bit is B2. Then we have the fourth AND gate, whose other bit is B3. So, this directly A0, B0 is your C0. This will come as a final output C0. Now, to get C1, you have to add B1 A0 with B0 A1. Okay. So, you have to give this as input for this another A1 line. Here also we have 4 AND gates. So this bit is B3, B2, B1, B0. So you have to basically add these 3 bits along with 0 and these 4 bits. Here basically I am going to perform. So by inserting a 0 here, so you can insert as many zeros as you want at the MSB position. I want to perform basically this 4-bit addition. So in order to perform this 4-bit addition, we can use 4-bit parallel adder such as ripple carry adder. So I am going to use here ripple carry adder. In fact, the fast adder is carry located adder. Actually, I have discussed about ripple carry adder, that is why I am writing. Otherwise, you can use the look ahead carry adder also. So the 3 bits are these, and these 4 bits are these. So the 4th bit of the first set of the number is 0. Okay. So this addition will be performed by this 4-bit triple carry adder. So directly the last bit will be your C1 bit. So here whatever this, the sum bit of this one is C1 bit, and the carries will be propagated inside this, because this is ripple carry adder. So the carry from this addition will be propagated to this addition will be propagated to this, and so on. That will take place inside, and the remaining 3 bits, totally you will get 5 bits. Okay, you will get remaining 4 bits along with the carry. So total this is sum bits, and this is carry out. Total 5 bits will be available. In that, 1 bit will be directly taken as the output. The remaining 4 bits will be given to. Then here I can insert a 0. Then I will perform addition of these 4 bits from here to here using another ripple carry adder. This. Okay. For that, this is one set of the numbers. Four-bit ripple carry adder. The second set of the numbers will be B3A2, B2A2, B1A2, B0A2. This can be generated through. So this line is A1 line, this is A2 line. So along with this A2, you have to generate 4 signals through 4 AND gates. This is one AND gate, second AND gate, third AND gate, fourth AND gate. So this bit is common. The other bits are here. This bit is B3, this is B2, this is B1, and this is B0. Then you will get finally this carry out. Total 5 bits you will get. Here the 4 bits, sum bits. This is carry out, this is sum bits. So these sum bits will act as C2, C3, C4, C5, C6. This is the final implementation of a 4-bit by 3-bit multiplier using 2 4-bit ripple carry adders along with 12 AND gates, 2 input AND gates. Okay. Now because we have already written the code correspond to this 4-bit ripple carry adder, we have to instantiate that code. Okay. So basically you call these outputs of these AND gates as wires. Okay. So this is basically C0 is directly the output. Okay, no need of wire here. So the remaining we require the wires. So we can call this wire as W1, W2, W3, W4, W5, W6, W7, W8, W9, W10, W11. this wire you have to define, and in addition to that this also you have to define as a wires. Okay. Let us call this one as P3, P2, P1, P0. So now what will be the Verilog code correspond to this one? So if I take this whole block, a 4 bit by 3 bit multiplier, if I consider as a whole block, this is 4 bit by 3 bit multiplier. What are the inputs and outputs? We have one 4 bit number input, B3, B2, B1, B0. This is block diagram. Inside this we will get that circuit we have discussed in the earlier slide. This is A2, A1, A0, one 4 bit number, another 3 bit number. Then we have 7 outputs, I think. So totally 7 outputs. C0, C1, C2, C3, C4, C5, C6. This is the block diagram of 4 bit by 3 bit multiplier basically. So we can define this as a module. I will give the name as multiplier. So what are the inputs and outputs of this multiplier? So we have the outputs C6 to 0, then inputs are A 2 to 0, B 3 to 0. Then output C6 to 0, input A 2 to 0, B 3 to 0. Okay. Then we can instantiate, or before that we will generate all the wires. Okay. So what are the wires? Wire 1 is directly C0 is the output. We will get C0 output through the AND gate. So we will get C0, and after that the wires are this W1, W2, so on up to W11. We can generate through this A0, B1, A0, B2, A0, B3, similarly A1, B0, A1, B1, so on. Okay. So here of course this carry in has to be 0, the same carry in has to be applied to this also. This carry in is equal to 0. So I will define first AND operations. I will get directly C0 through this one, OR. Output of the OR gate is C0, which is one of the output of the final 4 bit by 3 bit multiplier. The inputs are A0, B0. We have to define here wire. So totally we have W 11, 1, and then we require one more wire which is P 3, 0. These are the 2 wires required, right? So these wires are required, these wires are required. Okay. So I have got C0 output. Then I will generate the remaining all wired signals. Or C1 is nothing but B A0 with B1, or C2 is nothing but A0 with B2, or C3 is nothing but, this is W1, W2, W3. This is W1, W2, W3, A0, B3. Because these are the wires. This is W1. This is C0 is the first output, the remaining all are wires. So, you have not obtained the outputs, we have to obtain through the 4-bit triple carry adders. This is W1. Then W1, W2, W3, then we have similarly W4 is nothing but A1 with B0, W5 is A1 with B1. You can give the names actually here. You can give this as a name G1, G2, G3, G4, G5, G6, G7, W6 comma A1 comma B2 or G8, W7 comma A1 comma B3 or G9, W8 comma A2 comma B0 or G10, W9 A2 comma B1 or G11, W10 A2 comma B2 or G12, W11 comma A2 comma B3. This will generate all the wires. So, up to here. Okay. Now, to get P3, P2, P1, P0, you have to instantiate this 4-bit triple carry adder. To get the final result, you have to instantiate this, okay, with the Cin is equal to 0. Okay. So, we can assign Cin is equal to 0, we can take this as input, even you can define this wire for this Cin also otherwise, because this is not external to this block. So, I am defining this wire as a Cin. So, I will assign Cin is equal to 0, then you have to instantiate. Triple carry adders. I will give this module as M1, similar to the previous example. This I will call as M2. For M1, what are the inputs? So, the name that I have given for the code of the RCA is 4-bit underscore RCA M1. So, what are the outputs and inputs of this? Outputs are P3, P2, P1, P0, and you will get of course some here C out, sorry, including the C out only. This is P3, P2, P1, P0, because this is C out. Okay. So, P3, P2, P1, P0. So, outputs are P3 comma 0. The inputs are Cin is the one input. The other inputs are, this is 0. You can call this one as some X signal, say X also will create, because this is internal. I will define X also wire and I will assign X is equal to 0. Then X, W3, W2, W1 is one set of the numbers. Another set of the number is W7 to W4. X, I will define X as a wire here. Assign X is equal to 0. So, X is one input, Cin is another input. The other inputs are X comma W3, W2, W1, W0. Then we have W4, W5, W6, W7. So, this will produce P3, P2, P1, P0. Okay. Then again you have to instantiate this 4-bit triple carry adder, whose name I have given as M2. Now, what are the outputs and inputs of this? So, the inputs are Cin is there again, same Cin, and then P3, P2, P1, P0 is one set of the input, W11, W10, W9, W8 are the other inputs. Then the final outputs are C6 to C2. So, for this triple carry adder, C1 is also output. You can write C1 also as the output. Here you have to write C1 also, comma C1, because C1 is also output. Okay. then the output, final outputs are C6 to C1, C0 already generated. So, remaining are C2. These are the inputs. Outputs, the inputs are C in is one input, then P3 comma 0 are the other inputs, this P3 comma 0, then C in, and we have W 8 to 11, W 11 to 8. So, this will produce this C6, C5, C4, C3, C2. C1 has been produced in the previous 4-bit triple carrier adder, C0 through this AND gate. So, now I have got all the outputs. So, this is AND module. Okay. Here you have got C1 output, here C2 to C6, and here you have got C0. Okay. So, total this C6 to C0 will be generated. Okay. This is how we can use same 4-bit ripple carry adder even to implement a multiplier also. Okay. So, we have discussed a 4-bit by 3-bit multiplier. In a similar fashion, we can design any multiplier. In general, n bit by m bit multiplier. N and m can be any values. Okay. So, we can implement this by using basically ripple carry adders. Okay. So, in fact, this the multiplier that I have discussed is unsigned multiplier. I have not considered the signs, but in general in microprocessors and the DSP processors, normally you will use signed multipliers. Okay. So, signed multipliers we may discuss while discussing about the behavioral modeling. Okay. And the next arithmetic block is we have discussed about the adder subtractor, we can combine in a single block. Then we have discussed about the multiplier. Okay. The next arithmetic operation is division, but division is not a combinational circuit, we are discussing about the combinational circuit. So, this division also actually we will discuss while discussing about the behavioral modeling, because division circuit is somewhat complex. Okay. So, with this arithmetic operations, what are the next arithmetic operations is another important arithmetic operation is the comparison. So, the circuit which perform the comparison operation is called comparator. So, how to design a comparator? So, I will start with a single bit comparator and then I will go to the higher order comparators by instantiating the lower order comparators. Okay. So, if I take 1 bit comparator, there are two numbers A and B, only single bit, this is A naught, this is B naught, this is LSB bit and MS bit itself, only one bit. So, a comparator is a logical circuit which compares the two numbers, and the outcome of this comparator is 3 outputs. So, what are the 3 outputs? One is equal, another is greater, the third one is less. Okay. So, if I compare this A and B, so what are the possibilities? A can be equal to B, I will call this one as E0 because I am using only 0. A can be greater than B, I will call this one as G0. A can be less than B, this is L0. So, these are the outcomes of the comparison operator, outcomes of a comparator operation. Okay. Now, what will be the circuit diagram for this E0, G0, L0, how do you realize these signals? Okay. For that, because this is 1 bit logic, this is a simple logic. So, we know that exclusive NOR gate, this is the circuit diagram. Exclusive NOR gate will act as a equality detector. This is exclusive NOR gate, this will act as a equality detector. If I give A0, B0 as the input, you will get output as E0. E0 is equal to 1 if A0 is equal to B0, otherwise 0. This is equal to 0 if A0 is not equal to B0. This you can easily verify. So, exclusive OR is nothing but A0 exclusive NOR with B0, this is the exclusive NOR operation. A exclusive OR B is, this is the operation. This is A0 B0 bar plus A0 bar B0, whereas this is A0 B0 plus A0 bar B0 bar. So, if I take the truth table, A0 B0 and then A0 exclusive NOR with B0, 0 0, this is 0 0 1 1 1, 0 1 0, 1 0 also 0, 1 1 is, this will becomes 1, so 1. So, if the input bits are equal, output is 1, otherwise output is 0. So, this exclusive NOR gate acts as a equality detector. So, basically exclusive NOR gate will be used for checking the equality. Now, how to check A greater than B? So, A greater than B implies only one bit is there. So, A naught should be greater than B naught. So, this A naught and B naught are can be 0 or 1. So, A naught is greater than B naught implies A naught is equal to 1, B naught is equal to 0. So, to get G0 greater than equal to 1, this is equal to A0 B0 bar. Okay. So, if A is greater than B implies we will get G0 equal to 1 and G0 is equal to 0 otherwise. Whether this is equal or less than, G0 is 0. If A is greater than B, G is 1. So, how to implement this? Only one bit. This is basically the expression for the greater than operation is A0 B0 bar. Okay. So, you take A0 as it is and B0 through NOT gate, you apply to the AND gate, this will give G0. So, G0 is equal to 1 if A0 is greater than B0. A0 itself is A here because single bit. Similarly, you can obtain this less than as A is less than B implies A0 is 0, B0 is equal to 1. So, implies less than operation. If I write L0 is nothing but A0 bar B0. This is just complement of that of this greater than. So, this we have to take with complement, this you have to take without complement. This is less than. L0 is equal to 1 if A0 is less than B0, that implies A is less than B because only single bit number. So, this is the basic circuit diagram of a 1 bit comparator. Okay. So, we have 2 bits as the inputs and the 3 outcomes equal, greater than or less than. Okay. So, how to write the code here? Let us see a very simple, okay, Verilog code for this one is. So, you can define module 1 bit under comparison. I will give the name as 1 bit comparator. The outputs are E0, G0, L0, inputs are A0, B0. Output E0, G0, L0, input A0, B0. XNOR, I give name as gate 1, output is E0, input is A0, B0. And you have to define 2 wires also. You call this one as W1, W2. Wire W1 comma W2. Not W1, the input is B0, not wire is W2, input is A0. Now, using these wires, so the greater than operation will be and give this as G2, G3, G4. The output of the AND gate is G0. The inputs are W1 and A0. And G5, output is L0, input is W2 and B0, end module. This is a basic Verilog code correspond to 1 bit comparator. Okay. Now, actually in order to synthesize the circuit in a easier manner, so we have to construct the bigger circuits using smaller circuits. So, if I take this as a block diagram, this is equivalent to say block diagram. So, the inputs are A0, B0, outputs are E0, G0, L0. This is 1 bit comparator. Okay. If I can construct the 2 bit comparator using 2 single bit comparators, I can instantiate this program. So, I have given the name as 1 bit comparator. Okay. So, the inputs are A0, B0, outputs are E0, G0, L0. Okay. So, how to realize a 2 bit comparator? So, we will proceed in a progressive manner to the higher order comparators. 2 bit comparator. So, A is a 2 bit number, A1, A0, A1 is MSB, A0 is LSB, B is B1, B0, B1 is MSB, B0 is LSB. Now, to check A is equal to B. So, what are the condition for A is equal to B? A is equal to B if A0 is equal to B0 and A1 is equal to B1. Then only we can say that A is equal to B. Okay. So, we have 2 bits, both the bits has to be equal. Okay. So, how to check this equality? How to check this equality? We have called this one as that implies. So, the expression for the equality I will call as E2, because this is 2 bit comparator, I will call as E2. E2 is equal to check this equality, this is E0, to check this equality E1, where what is E0 and E1? E0 is exclusive NOR between A0 and B0 and E1 is exclusive NOR between A1 and B1. So, basically E2 is E0 into E1. Then A less than B or A greater than B, it is up to you. A greater than B, how to check A greater than B? We have 2 numbers. If, what are the 2 conditions? We have 2 conditions. One is if A1 is greater than B1, regardless of A0 and B0, it is sufficient to say that A is greater than B, okay, because this MSB bit. So, A is a 2 bit number, A1 A0, B is a 2 bit number, B1 B0. If I assume that this is 1, this is a do not care, this can be 0 or 1. So, A1 is greater than B1 means A1 is 1, B1 is 0, this is 0, this is even, this is 1, if this is even 0, the least value. So, in any case A is greater than B. So, if MSB bit of A is greater than the MSB bit of B, it is sufficient to say that A is greater than B. This is one condition. Or, so what is the second condition? If A1 is equal to B1 say, then and if A1 is equal to B1, then A0 should be greater than B0. These are the only 2 conditions under which we can say that A is greater than B. Okay. So, what is the Boolean expression for this? If I call this as G2, this is equal to, what is this? This is G1. Okay. This is G1 expression, or if you want you can write in Boolean expression A1 greater than B1 means A1 B1 bar. And what is this? This is nothing but E1, this is R, R means R, okay, plus this is E1 and this is and A0 greater than B0 means A0 B0 bar. So, this is the expression for G2. Similarly, the third condition A less than B, if under two conditions similar to this, if A1 is less than B1, it is sufficient to say that A is less than B, or second condition is if A1 is equal to B1 and A0 is less than B0. These are the two conditions under which we can say that A is less than B. So, what is the condition for this output L2? If I call as this is equal to A1 less than B1 means A1 bar B1, this is R, plus A1 B1 means this is E1. I have defined what is E1 here, and A0 bar B0. So, these are the expressions. Okay. And for 1 bit comparator, what are this? For 1 bit comparator, we have taken A0 B0 as this one. A0 B0, and you have got three expressions E0 G0 L0, E0 G0 L0. This is 1 bit comparator. So, what is the expression for E0 we have obtained is A0 exclusion OR between B0, and G0 is A0 B0 bar, L0 is A0 bar B0. Similarly, I will take another 1 bit comparator, and I will give the inputs as A1 B1, and I will call the outputs as E1 G1 L1. So, what are the expression for E1 is A1 exclusion OR with B1, G1 is nothing but A1 B1 bar, L1 is equal to A1 bar B1. Now, I have got this expression. Now, how to implement this overall E? So, this E0 E1 AND operation is nothing but E. So, this E2 we will call as E2, output of this 2 bit comparator we are calling as this as E2, this as G2, this as L2. So, what is the expression for E2? E2 is nothing but E0 E1. We just AND these two operations, you will get E2. This is E2 is the output of this 2 bit comparator. Now, how to get G2? G2 is nothing but A1 B1 bar. A1 B1 bar is nothing but G1. So, this you can write as G1 plus E1 as it is, and what is A0 B0 bar? Sorry, this A0 B0 bar is G0. So, the expression for G2 is equal to G1 plus E1 G0. Okay. So, G1 plus E1 G0, E1 G0. So, this G0, this E1, this is G0 E1 plus G1. If we are with this one, you will get G2. Similarly, to get the expression for L2, A1 bar B1, A1 bar B1 is this, which is L1, this is equal to L1 plus E1. What is A0 bar B0? A0 bar B0 is L0. So, that E1 into L0. Okay. So, you can get this L2 as E1 L0, L0 and E1, L0 is this and E1 is this. These two you have to AND, then you have to OR with L1. This is your L2. So, by instantiating this 1 bit comparator twice using some additional gates, we can implement a 2 bit comparator. So what will be the code for respect to this 2-bit comparator? Module, I will call as 2-bit comparator. 1-bit comparator I have given as 1-bit CMP. So what are the outputs and inputs of this 2-bit comparator? We have 4 inputs and 3 outputs. Outputs are E2, G2, L2, comma. Inputs are A 1:0, B 1:0. Then first you have to instantiate this lower order modules. Of course, we require some we can define output and input. Outputs are E2, G2, L2. Inputs A120, B120. Because if I write this as a block, this as a block, these are 4 inputs and 3 outputs. This is 2-bit comparator. A1 A0, B1 B0. This is E2, G2, L2. Okay. So these are the inputs outputs I have defined. Now we have to instantiate 1-bit comparators. So the name that I have given is 1-bit underscore comp. We call this as module 1 M1, we call this as module M2. M1, what are the inputs and outputs of the module 1? Outputs are E0, G0, L0. Inputs are A0, B0. So this will perform this and this will give outputs as E0, L0, G0. Okay. Then you have to write another 1-bit comparator M2. The outputs are E1, G1, L1, comma A1, comma B1. Of course, you have to define this E0, G0, L0, E1, G1, L1 as a wire. Okay, you can write somewhere here wire E0, comma E1, comma G0, comma G1, comma L0, comma L1 as a wire. Okay. Then these 2 1-bit comparators we have instantiated. Then final result to get E2. So what is the expression for E2? E2 is nothing but E1 E0. Okay, we have to take AND gate. AND gate whose you call this as G1, gate 1. Output is E2. Inputs are E1 and E0, which we have generated using these 2 1-bit comparators. We have defined these as wires. So E2 has obtained. To obtain G2, G1 plus E1 G0. So first you obtain E1 G0, you call this one as some other wire W1, this you call as W2. So we can define here W1, W2 also wires. So you perform AND operation G2. Output is W1, inputs are this is G0 and E1, G0 and E1, this G0 and E1. Similarly, AND G3, W2, this E1, L0, L0, comma E1. Now once if you obtain this W1 and W2, so G2 is nothing but G1 with W1, L2 is nothing but L1 with W2. Okay. OR gate, G4, G2 is the output which is greater than output. The inputs are W1 and G1. OR G5, L2 is the output. To get the L2 output, this I have defined as W2, the other one is L1. This L1 we have defined as a wires which we have generated using this 1 bit comparators. So, we have got the final 3 outputs, greater than, less than and then equal, E2. Okay. This is end module. This is how we can construct the larger comparators, knowing the lower comparator codes. Okay. Now, I will extend to the 4 bit comparator. I will just explain the theory. So, you can write in a similar manner the Verilog code. So, 4 bit comparator. This you can construct using 2 bit comparators. So, basically A is having 4 bits, A3, A2, A1, A0. B is having 4 bit numbers, B3, B2, B1, B0. Here A0, B0 are LSBs and A3 and B3 are MSBs. Okay. So, A is equal to B. How to check this? If A3 is equal to B3, comma A2 is equal to B2, A1 is equal to B1. This is all ANDs, you can call as this is and A0 is equal to B0. So, this we are calling A1 A0 as, this implies if I call this as E finally, and if I call this one as E3, A2 is equal to B2 if I call as E2, E1, E0. Okay. Where E3 is equal to A3 exclusive NOR with B3 and so on. A greater than B, if I call this as E, this as G finally. So, if what is the condition? There are 2-3 conditions. One is if A3 is greater than B3, it is enough to say that A is greater than B. If otherwise, or what is the condition? Second condition, if say MSB bit is equal, and if A2 is also greater than B2, it is enough. Or if first 2 bits are same, A3 is equal to B3 and A2 is equal to B2, then the next bit has to be greater than, A1 is greater than B1. Or the last term in condition is if the first 3 bits are same, A2 is equal to B2 and A1 is equal to B1 and A0 is greater than B0. These are the conditions under which we can say that this A is greater than B. So, what is the expression for G if I call this as a G? So, directly as it is, this I will call as G3, or you can directly write the expression. So, A3 greater than B3 means A3 B3 bar. This or you have to just map this statement onto the Boolean expression. Or means place A3 is equal to B3 is E3, A2 greater than B2 means A2 B2 bar, or A3 is B3 is E2, A2 B2 is E2 and A1 B1 bar plus E3 E2 E1 E0, E3 E2 E1 and then A1 B0 bar, A0 B0 bar. This is the expression for G. Okay. Similarly, if I take the less than expression, A less than B. So, what are the conditions? If one condition is A3 should be less than B3, or second condition is A3 is equal to B3 and A2 is less than B2, or third condition is A3 is equal to B3 and A2 is equal to B2 and A0 is A1 is less than B1, or the fourth condition is A3 is equal to B3 and A2 is equal to B2 and A1 is equal to B1 and A0 is less than B0. So, the expression for less will be A3 bar B3, R is place E3, A2 bar B2, R is place E3 E2, A1 bar B1 plus E3 E2 E1 E0, sorry, A0 bar B0. Okay. Now, we can construct this 4-bit comparator using two 2-bit comparators by appropriately defining these values. Then you can instantiate 2-bit comparator twice, and with some external gates such as AND and OR gates, we can construct this 4-bit comparator. Okay. So, see about this the next arithmetic circuit, which is a 4-bit comparator. Okay. So, next we will discuss some of the control blocks such as decoders, encoders and all. Thank you.